Okay. Hello, guys. Welcome to today's post contest discussion of the Codeforces round. Right? Today, we'll be discussing problems A, B, C, D, and E. I started giving contests after quite some time that were rated for me, and this was one of those contests which went well. So, let's get started. Very interesting ideas in all five problems. Very simple solutions to all the five problems. Before getting started, TLE 12.0 is live. So if you do enjoy our post contest discussions, you can definitely check them out. Link in description. That being said, let's get started. Problem A. Problem A says that, guys, you are given a non-increasing array. Okay, this is what the problem says. You are given a non-increasing array and using some operations. Okay, what operations? Make in one operation, you can have an HI, change it to any value X. So using these kind of operations, you have to make it non-decreasing. Okay, this is what the problem says. Let me take a few examples and show you what the problem actually means. Okay, so guys, oops, 1 second. So sorry for that. Yeah. Now, guys, the problem says that we are given a non-increasing array. What is a non-increasing array, guys? It is a descending array. Okay. And the size of this array is n. We have to convert it into an ascending array. All right. Of size n. And to do this, what can we do? We can do an operation. And what operation is this? Choose an index I and an value X and then make HI is equal to X. Okay. For example, and we need to find the minimum number of operations to do so. In something like 1, 2, 3, what you can do is, you'll be given 3, 2, 1. So in something like 3, 2, 1, you can make this into a 4, make this into a 5. So the array becomes 3, 4, 5. The number of operations to do so is 2. So guys, how do you go about solving this particular problem? Okay. Guys, we are given a descending array. Yes or no? And we need to make it into an ascending array. Okay. Let's take a simple example. Let's take something like 3, 3, 2, 2, 2, 1, 1. Okay. Now, guys, if we wanted to make this array ascending, let me just make commas. If we wanted to make this array ascending, guys, do you all agree that we can select any one number that we want to keep constant? Okay. For example, let's say we didn't want to change 2. So do you agree I can keep all occurrences of 2 as it is? Yes or no? Yes or no, guys? Tell me. Yes, now. All elements that are on the right side of 2, they are currently smaller than 2. Okay. We need to make all those elements greater than equal to 2. Similarly, all elements on the left, they are greater than 2 currently. We want to make them smaller than equal to 2. Do you guys agree for all elements on the left, we can make it equal to 2. And for all elements on the right, we can make it into a 2. And now we have an ascending array. Yes or no, guys? If I convert this to a 2, 2, and if I convert this to a 2, 2, we can make this array ascending because if all elements are equal, the array is ascending. Yes? Okay. So guys, the thing to notice here is that what are we going to change? Which elements did we change? We changed those elements which were not equal to 2. Yes or no? You saw that there were some elements not equal to 2, so we changed them. Now, let's iterate over all possible values. Okay, 3, 2, 1. Let's see how many operation it takes. So the array is 3, 3, 2, 2, 2, and 1, 1. Let's see the number of operations it takes if we want to make all elements equal to that number. So if we want to make it equal to 3, the number of operations is going to be 5. If we want to make it equal to 2, the number of operations is equal to 4. If we want to make it equal to 1, the number of operations is again equal to 5, because apart from these one, we'll be changing everything else. These numbers are not random, guys. What is this? It's just the number of elements minus frequency of that particular element is the answer if we make all elements equal to x. For example, if we wanted to make all elements equal to 3, we change all elements that are not equal to 3, right? So n minus frequency of 3. Frequency of 3 is 2. So 7 minus 2 is 5. Similarly, if we want to make all elements equal to 2, then n minus 3, which is 4, and similarly 1. Now, we want the minimum possible one. So we can say that we are going to pick x such that the frequency is as high as possible, because if we make frequency as high as possible, n minus frequency is going to be as low as possible. Is this clear for everyone, guys? Yes. What I'm trying to say is our answer, if we want to change all elements equal to x, is n minus the frequency of x. So we want the frequency to be as high as possible. So we'll pick the element with the highest frequency, and our answer is going to be n minus frequency of the most occurring element. Is this clear for everyone? So let me just reiterate. We just find max frequency, and our answer is going to be nothing but n minus max frequency of an element. Is this clear for everyone, guys? Tell me, put a yes in the chat if it is indeed clear. Okay. Ankita says it is clear. What about Sukumar? Great. So guys, let me just quickly show you the solution. That is all that we had to do. You take in input. After that, you find the frequency of all elements. You can do that using a map. After that, you have a variable called frequency. Then max frequency is nothing but maximum of the current frequency, comma, the frequency of the element. So basically we iterate over the map, find the max frequency, and then the answer is nothing but n minus frequency. A very simple big O of n log n solution. If that much is clear with everyone, let's move on to problem B. Problem B is actually very, very simple. It seems hard, but trust me guys, it's not hard. Okay. What does the problem say? The problem says that you are given a permutation of length n. What is the permutation? The numbers are 1, 2, 3, 4, 5, 6 up to n. All elements occur exactly once. We need to make this sorted. And for sorting this, guys, what can we do? We can select an index such that pi plus 1 minus pi is equal to 1. What does this mean? If the absolute difference between the two elements is equal to 1, let's say the current element is 3. So if the previous element is 4 or previous element is 2, then we can swap them. Okay. We need to find if it is possible to sort the permutation P such that Satay sticks. Basically, using these constraints, are we able to sort these elements or not? Okay. Now, guys, let me show you how we can solve this problem. Let's take an example test case, which is 2143. Okay. Let's take 2, 1, 4, 3. Guys, what is the constraint given to us? Okay. The constraint given to us is that for I and I plus 1, if pi, absolute of pi minus pi plus 1 is equal to 1, then what we can do, we can swap I, ARR of I and ARR of I plus 1, or P of I and P of I plus 1. Isn't this what the problem statement says? Yes. So here you can see that we can swap these two, okay? And we can swap these two. And after doing that, our array will become 1, comma 2, comma 3, comma 4. Okay. Now, guys, we are going to use, like, to solve this problem, this basically tests how good your understanding of sorting is. Okay. You don't really need to do anything special here. I have a very simple solution. Guys, the thing I want you all to notice is that if you wanted to sort this array as it is, okay, 2, comma 1, comma 4, comma 3. Let's try to actually sort it, okay? And the question says that we are swapping adjacent elements, okay? We are swapping adjacent elements. Can you tell me which sorting algorithm makes use of swapping adjacent elements? There are many, but there is a very famous one, right? There is bubble sort, there is insertion sort, yes or no? Okay, let's look at insertion sort. What is basically insertion sort? Let me just show you and I'll explain why and how our solution works. Okay, guys, let's have our array empty. Okay, and after our array is empty, let's introduce numbers one by one. Okay, we have initially 2. All right. For the elements we have introduced, is the array sorted? Yes, right. It is sorted. Now, since this is sorted, let's introduce the next element, which is 1. So after we introduce 2, 1, you can notice that our array is not sorted. So now we'll need to swap 2 and 1. And after swapping 2 and 1, you will notice that our array is sorted. Okay. 1, 2. And why did this happen? Because 1 was smaller than 2. Now we will introduce 4. You can see that the array is already sorted. So we'll introduce 3. You can notice that 3 is smaller than 4. So we will need to swap these two. So we will swap 3 and 4 and our array becomes 1, 2, 3, 4. Is this idea of sorting clear with you guys? Basically, what are we doing? We are introducing new elements, and after introducing those each element, we are performing the swaps. This is known as insertion sort. Basically, you insert one element and then you keep swapping till it reaches its position. Is this clear with everyone? We introduced 2, then we introduced 1 and made those swaps. It became 1, 2. Then we introduced 4. Our vector became 1, 2, 4. And after that, we introduced 3. But since 3 is smaller than the last element, 4, we performed some swaps and made the array sorted. Is this clear with everyone? Tell me, guys. Okay. Now, if you look at this algorithm carefully, what did we do, guys? We introduced a new element. Okay. Introduced a new element. Okay. And till this element, okay, till this element is smaller than previous element, keep swapping. Okay, keep swapping. Isn't this our more or less idea, guys? For example, if it is 2, 3, 4, 5, 1, then these elements will be as it is. So 2, 3, 4, 5, 1. And after that, when we introduce 1, we swap this, so it becomes 2, 3, 4, 1, 5. Then you swap this as well, swap this as well, swap this as well. So finally, you keep pushing 1 towards the left, and the array becomes 1, 2, 3, 4, 5. Is this algorithm clear with everyone? Yes, I've not gotten to the problem yet, Ankita. All right, I'm just explaining how sorting works, and then I will show you how we can use this in our problem. Okay. Okay. Now, guys, if this algorithm is clear, the only new thing that is introduced is we can swap. Okay, we can swap only if the difference between them is a uh, is the absolute difference between them is 1, correct? So guys, the thing to notice here is that you are going to swap 1 with 5 when 5 is greater than 1. Yes or no? So if and 5 is greater than 1, correct? Now the constraint given to us is if x comma y you are swapping, then absolute of x minus y is equal to 1. But guys, we are only swapping when x is greater than y. So guys, when we are swapping, x is greater than y and x minus y absolute is equal to 1. So can we just say that x is equal to y plus 1? Because if you look at the sorting algorithm, we are only swapping 5 and 1 when 5 is greater than 1. And the constraint that is given to us is you can only swap when the absolute difference between them is 1. So if you just look at these two constraints, can we just say that x is equal to y plus 1? That is the only condition when this is going to take place. Yes or no? Yes. So guys, that is all that you needed to solve for this particular problem. When your previous element is 1 greater than your current element, you need to perform the swap operation. And in the end, you just need to check if it is sorted or not. Just to reiterate, what were we doing? We were doing a simple insertion sort, and the only thing we need to check if x is greater than y and absolute of x minus 1, y is equal to 1. So we just implement exactly that. And you can see that this is very simple. You take in the input, you start from the second element. If ai minus 1 is equal to minus 1, which means that ai minus 1, the previous element is equal to the current element plus 1, as we deduced. So if that is the case, if x is equal to y plus 1, in that case, you just swap the current and the previous element. A thing to notice here is that there is only going to be one element which is equal to uh, y plus 1. So if you have a current element y, if the previous element is y plus 1, no other element can be y plus 1 because this is a permutation. So you need to only perform one operation for each element. And in the end, you just check if the array is sorted. So you can just run a for loop, or you can have a inbuilt function called is sorted, which given a range checks if it's sorted or not. So that's all that you have to do. And in the end, you just check if it's sorted. If it is, you just print yes, otherwise you print no. Is this clear for everyone? We just used simple insertion sort. After that, we saw that there is a new constraint on the swapping. So we just introduced this and got this done. Would bubble sort work here too? Bubble sort would work here too. You will have to come up with your own constraints and solve it accordingly. I just noticed that in insertion sort, you keep introducing a new element and swap. So with that being said, and the constraint that is given to us, the only constraint when we can actually swap is that the previous element is equal to the current element plus 1. If that is the case, you swap the previous and the current. If these are the only swaps that are happening, after performing all possible swaps, you check if the array is sorted. If it is sorted, you print yes, otherwise you print no. Is this clear for everyone, guys? Isn't this a very, very clever kind of solution? We didn't need to figure out a lot of things. We could rely on sorting algorithms that computer scientists made for us, that is insertion sort. That is, you just introduce elements one by one and keep swapping, and there is a constraint given to us that you can just follow, and if we make swaps like that, you can, in the end, you just need to check if it is sorted or not. Is this much clear for everyone? Tell me, guys, put a yes in the chat if it is indeed clear. If you have any doubts, feel free to ask for the same. Okay, I'll just wait for a couple of minutes. You can take your time, and at, let's say, 8:50 or 8:51, I'll move on to the next problem. Okay, great. Ankita, I'll have to look into it. You can feel free to ping me on Discord. I'll definitely look into bringing up a counter example for you post the post contest session. Okay, great. Now, guys, let's move on to problem C. I think this problem is clear for everyone. It's called Penchick and BBQ Buns. This is a good problem. It's kind of those problems. It's kind of those mind puzzles that you have to solve. It's not actually a programming problem. It's like a puzzle. So let's look at the problem. Penchick loves two things: square numbers and Hong Kong style BBQ buns. Okay, this is not really necessary. Let's have a look at what the actual problem is. Okay, there are n BBQ buns arranged from left to right. There are 10 raised to 6 available fillings for each BBQ bun, numbered from 1 to 10 raised to 6. To ensure that Penchick would love this gift, Cohen has few goals. No filling is used exactly once. This means that a filling is either used 0 times or greater than equal to 2 times. After this, for any two buns I and j that have the same filling, the distance between them, that is absolute of I comma j, okay, must be a perfect square. This is what the problem says. Let's have a look how we can go about solving this particular problem. Okay, this is a very good problem, not in terms of algorithms, but in terms of thinking. This is the problem I solved after problem D in the contest. So what is the problem C, guys? That each filling, okay, each filling cannot be used one time, okay, cannot be used one time, okay. Apart from this, okay, apart from this, if you have, let's say, for a filling, if you have elements x, y, then absolute of x comma y should be a perfect square. Okay, for one particular filling, if you have two positions where this filling was used, let's say x, y, then x minus y should be a perfect square. If you have three elements, then all pair should form a perfect square. Is this much clear for everyone, guys? We have to come up with an array that satisfies these constraints, or print -1 if it is not indeed possible. So guys, the first thing to notice here is that what are perfect squares? Let's write some things down. You have 1, you have 4, you have 9, and then you have 16. Okay. Guys, do you notice this? You have 1 as a perfect square. What does this mean? This is very, very important. What does this mean? It means that if I have an array of size 2, I can put filling 1 here, filling 1 here, and this magically becomes valid. Why? Because I placed the filling 1 next to each other. So the distance between them is 1, which is a perfect square. Does this make sense? Okay. If this does make sense, guys, now instead of 2, let's say we had 4 elements. Do you agree we can have 1 1 and we can have 2 2? If you look at any filling, each filling has been used either 0 or greater than equal to 2 times. And if you look at the absolute differences between the distances of each filling, this is 1 and it's a perfect square. This is 1 and this is a perfect square. Okay. So for 2, we are able to come up with this. For 4, we are able to come up with this. For 6, we can similarly come up with a code like 1 1 2 2 3 3. Okay. So guys, is this, can you notice that for n, when n is even, we can just solve it as 1 1 2 2 3 3 and so on and so forth. Yes or no, guys? Tell me, when n is even, you can just make pairs like 1 comma 1 2 comma 2 3 comma 3 4 comma 4, so on and so forth. And since we are able to make pairs, for solving it for even n is relatively easy, correct? Is this much clear, guys? Okay. If this much is clear, let's go to solve it for odd n. Okay. And let's see how to solve it for odd n. The first thing to notice here is, guys, for odd n, okay, do you agree we can't make pairs like this? Okay, we can't make pairs like this because one element, okay, one element will be left out. Okay, one element is going to be left out. Yes or no? So for odd, we cannot use a strategy like this, but what can we use? Since, guys, one element is going to be left out, let's make one triplet. Okay. And apart from that one triplet, everything else we can make as pairs. Correct? If we are able to make a group of 3 elements and then we can just keep pairing 2 2 2, we'll be able to come up with the answer. Now the thing is, how do we come up with this pair or this triplet? Let's have a look. So guys, for this triplet, let's say the positions are x, y, and z in sorted order. Do you guys agree y minus x is a perfect square? Okay. After that, z minus y is a perfect square. Also, z minus x is a perfect square. Yes or no? These three are perfect squares. Is this much clear for everyone? Okay. If this much is clear for everyone, do you guys notice that z minus x is nothing but y minus x plus z minus y? Yes or no? Yes. If you look at this on a number line, okay, let me help you visualize it. If you have x, y, and z, this is a perfect square, this is a perfect square, this is a perfect square. But guys, this right here is nothing but addition of y minus x plus z minus y. Okay. So guys, what does this say? This means that, let's say this is a perfect square. Okay. This means that, let's say this is A, this is B, this is C. Perfect square A plus perfect square B is equal to perfect square C. Yes or no? we can, like, let me make this simpler for you. A plus B is equal to C, or we can see that square root of A, where square root of A is an integer, plus square root of B, where this is an integer, plus square root of C, where this is an integer. This is what is followed. Yes or no? This can be written like this. Okay. Now, guys, what is this? This is nothing but Pythagoras theorem. Yes or no? A square plus B square is equal to C square is nothing but Pythagoras theorem, and the smallest Pythagorean triplet that is said to exist where all numbers are positive is nothing but 3 square plus 4 square is equal to 5 square. Yes or no? Can you come up with a smaller Pythagorean triplet where all numbers are greater than equal to 1? Tell me, guys. Yes or no? No, right? This is the smallest possible one. So we can say that 9 plus 16 is equal to 25. Okay. So guys, how do we go about solving this? Keep this in mind. We can have 9, 16, and then we can just join them. We can have a triplet like this. So let me just quickly spin up numbers 1 to 26. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. So guys, you have 1 over here. You have 2, 3, 4, 5. Okay. So we can have 5. We can have 10 over here. Okay. So you have 5, 6, 7, 8, 9, 10. This is 10 over here and this is 26 over here. Okay. If we make a triplet here, do you guys agree that this is one of the things that we were able to make? Okay. Now, between 1 and 10, what numbers exist? 2, 3, 4, 5, 6, 7, 8, 9. Okay. 8 number exists between 1 and 10. So do you agree we can just pair these two, pair these two, pair these two, and pair these two? Yes or no? We can just pair 2 and 3. We can just pair 4 and 5. We can just pair 5 and 6. And we can just pair so on and so forth. 2, 3, 4, 5, 6, 7, and 8 and 9. Okay. After this, guys, between 10 and 26. Okay. Between 10 and 26, there is a problem. What is the problem? We have odd number of elements. Okay. If you look at it, we don't have even number of elements because we have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have, guys, 15 elements. So one element is going to get left out and we need to do something. And let me draw 11 to 25 here. Okay. So 11, okay, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. Okay. So let's say we made this to a pair, this to a pair, this to a pair, this to a pair. Okay. 26 we cannot be used. It's already being used. Okay. Now we can make these to a pair. And now the thing you will notice here is that we are left with 5 elements and we can't make everything a pair. What do we do here? The very simple solution is, guys, you make these two a pair, you make these two a pair, and then you join 23 and 27. Because 27 minus 23 is 4, and 4 is a perfect square. So do you see how between 1, 10, and 26, we are able to come up with a triplet? After that, for all elements between 1 and 10, we are solving it separately. And for all elements between between 10 and 26, we are solving it separately. So the only thing that changed is we are having an edge from 23 to 27, or basically we are having the same filling for 23 and 27. Using this, guys, do you see that we were able to solve it for n is equal to 27? And now that you solved it for n is equal to 27, if we had 29, we can solve it for n is equal to 27 as it is, and then you can have two elements x and x. If it was 31, then you can have two elements. You can solve it for 27 as it is. You have x and x, and then you have y and y. So can you see, for all odd elements greater than equal to 27, for all n greater than equal to 27, we are able to solve it. And for all even numbers, we are able to solve it. Is this much clear for everyone? If this much is clear for everyone, let me share the code of the same. That is more or less it, that what you have to do. So let me show you the code. So just forget this. This is not actually 15. It should be named 27. In the contest, I made an error. I thought for some reason that 9 plus 6 is equal to 15. It should have been 9 plus 16 is equal to 25. So consider this. So these are basically 25 elements, and I have solved it for 1 to 27. Sorry, these are 27 elements, and I've solved it for 1 to 27. After that, uh, you just take in n. If n is even, then you just print pairs, that is 1 1 2 2 3 3 4 4, so on and so forth. If that is not the case, if n is odd and n is smaller than 27, then you print -1. Otherwise, your final answer is solving it till 27. And after that, what do? You have some number of elements that are left. So those many elements, you just keep pushbacking with pairs. So 14, 14, 15, 15, 16, 16, so on and so forth. And in the end, you just print out that array. So for even elements, you have a different solution. For odd elements, you have a different solution. Is this clear for everyone? This is a very clean code, right? And the only thing to notice is that you solve for 27. And after solving it for 27, you can solve it for any odd number. It can be easily proven that it's not possible to solve it for any odd number smaller than 27, because the smallest Pythagorean triplet, okay, ends at 25. And we saw that for 25, it's not so, if it ends at 25, then we have to take elements till 26, and 26 is even. So the next possible odd is 27. So we can indeed solve it for 27, and we can solve it for any odd after that. Is this clear for everyone? Do let me know in the chat what you guys were able to think. Okay. Okay. Do put clear in the chat, guys, if this problem is indeed clear for every one of y'all. If not, do let me know what doubts you have. We'll definitely get them resolved. Okay, great. Okay, I see that this problem is clear for majority of the people. Let's move on to the next problem, which is problem D, which is Penchick and Desert Rabbit. Okay, this is a very standard question actually. I like a lot of like 2000 plus people solved this problem, which is not always the case for a division 2D problem. And this was because this problem was relatively easy. What does the problem say? Dedicating to push himself to the limits, Penchick challenged himself to survive the midday sun in the Arabian desert. While trekking along a linear oasis, Penchick spots a desert rabbit preparing to jump along the line of palm trees. There are n trees, each one has a height AI. The rabbit can jump from the ith tree to the jth tree if exactly one of the following conditions is true. You can go backwards to a taller tree, or you can go forwards to a smaller tree. So what does this mean, guys? This means that if you're on a particular index I, then you can go backwards if you're on a taller tree. Otherwise, if you're going forward, you go forward to a taller tree, a shorter tree. Okay. For every index I to n, you need to determine the maximum possible height of jump that is possible for that rabbit if that rabbit starts on the ith tree. For example, let me show you a given test case. If you start at 3, then your answer is 3. If you start at 1, you can see that you can go backwards towards a more taller tree. So you can go to 3. For 2, how is the answer 3? Because you can go ahead, okay, to 1. And after that, you can go back to 3. Yes or no, guys? Tell me. Yes? Okay. So if this much is indeed clear for all of y'all, let me show you the solution of the same, or let me share the solution of the same. So guys, let's have a look at the problem. Okay, just give me 1 second. Okay, so guys, 21463857. Okay, 21463857. Okay, this is our array, guys. The first thing to notice here is that what does the problem say? The problem says that if you're on an index I, you can go ahead to a smaller tree. Okay, let's not look at any equations. You can go ahead to a smaller tree and you can go backwards to a larger tree. Okay, now, now for every index I, we want to know what is the largest tree we can possibly go forward to. Okay, that is what we want to know. Now, guys, I want to ask you all, if we are over here, which is the last element, do you agree that our answer, okay, is going to be either 7 or it is going to be the largest element on the left hand side? Yes or no? This is D, Harsh. Okay. So, guys, you can notice that for 7, the answer would either be 7 or the largest element for towards the left hand side. So for the 7, the answer is 8. Now guys, for 5, it is either going to be 5 or it is going to be um, something, the largest element on the left hand side of 5, which is 8 again. For 8, it is going to be 8. Now for 3, guys, for 3, how do we come up with 8 is the question. Okay. And can we actually come up with 8? So guys, you can notice for 3, we can go backwards to a smaller tree. We can go forward to a smaller tree and we can go backward to a larger tree. Okay. So for 3, guys, do you notice we can go to 6? Okay. And 6 is the largest element over here. Okay. After going to 6, we can basically go to 5. And after going to 5, we can find 8. Yes or no? Tell me, guys. So what are the operations that we did? If we are on any index I, okay, either the answer is the element, the ith element itself, okay. Otherwise, the answer is the largest element, okay, largest element on left hand side, LHS, okay. Or what is the answer, guys? What did we do here for 3? Can you notice for 3? We went to the largest element on the left. Okay. Then we basically, like, let's say there was a 1 here, there was a 2 here, so on and so forth. We checked for all possible values that are smaller than 6. We have 5, we have 1, we have 2. What is the maximum possible answer we can have? So guys, for 6, we could have gone to 5. And for 5, we already know what the answer is. So what did we do? We went to the largest element on LHS. Okay. After going to the largest element on LHS, on the right hand side, okay, on the right hand side of this element, we check for all possible smaller elements. What is the answer? Is this idea clear for you all guys? Like if we are at 3, the answer is either going to be 3 or it's going to be the largest element on the left hand side of 3. Otherwise, we go to the largest element, then on the right hand side of 6, we check for all possible values that were smaller than 6. Basically, here you have 3 and 5. If you are at 3, what is the possible answer? You can have 6 as an answer. If you are at 5, what is the possible answer? You have 8 as an answer. So here you have 6, here you have 8. Maximum of 6 and 8 is indeed 8. So for this element 3, our answer would again be 8. For 6, guys, you can notice that you are able to go to 5. And after going to 5, you are then able to go to 8. So one thing you can notice here is that you can also do one more thing. You can go to a smaller element, go to smaller element on RHS and then go backward. Yes or no, guys? Tell me. What are the things that we can do? If we are on index I, either this index itself is going to be the answer. Otherwise, you go backwards and the largest element that is there on the left hand side, that is going to be your answer. Otherwise, you go ahead to a particular index and after that you come back somewhere. Okay, these are the things that are going to be your answer. And last but not the least, you are going to go back, okay, to the largest element. After that largest element, you are going to check for all elements smaller than this largest element. What is the answer if we went back from these elements? And from all possible answers, we find the maximum possible answers. So do you guys agree these are the 4 conditions that we have that we can actually perform for this particular problem? Yes or no, guys? Tell me. 1 second. Let me see. Yes. Okay. So if this is clear, let's actually simulate this. Okay, guys, let's actually simulate this. And let me give you more understanding over this problem. So 21463857. So guys, for 21463857, let's solve it for 7 first. For 7, the answer is 8. Okay. And why are we solving it from right to left and not left to right? Because guys, our final operation that we perform is always a backward operation. Okay. Our final operation that is performed is always a backward operation. So our answer always tends towards the left. So for 7, our answer is 8. For 5, our answer is 8. For 8, our answer is 8. For 3, our answer is 3 or the maximum element on the left, which is 6. Or you go to 6 and then you go to some smaller element than 6 and then you go to a larger element. So 6, 5 and 8. So the answer here is 8. For 6, guys, again, you can go to a smaller element and then larger element. So 8. For 4, you can actually go to 3 and then you can go to 6 and then you can go to 5 and then you can go to 8. Okay. So you can directly go further. So you can go to 3 and this 3, you know that you can reach 8. So for this, the answer is going to be 8 because 4, 3, 6, 5 and 8. After this guys, for 1 you can see that you can go to 2, and after going to 2, how is this answer 8? One second. Is this 1, 2 or 2, 4? Okay, so there was a 4 here. Okay, never mind. So guys, this is 4 and this is actually 1. So for this one, you can notice that you can go to 4, then you can go to 3, and then you can go to 8. For this 4, the answer is 8. And for this 2, you can go to 1, and then you can go to 4, and then you can go to 3, 6, and 8. So the answer for all these elements becomes 8. So guys, because we are sweeping from right to left, okay, what do we notice? We want to know, like if we are at an element X, okay, we want to know the answer for all elements on the right hand side. Okay, so we know the answer for 3, 8, 5, and 7. Let's look at what we would do if we want to try to fix the answer for 4. Okay, let's say 4 is over here. Okay, guys, we know the answer for 6, 3, 8, 5, and 7. Now, if we are at 4, we can either go to a larger element on the left. Let's say it does not exist. Okay, so it does not exist, so answer does not exist. Or we can take 4 itself, or we can go to a smaller element on the right hand side, and then we already know for those smaller element what is the answer. Now let's say we had a 2 here and a 1 here, whose answer was 6 and 5. So you can notice you can go to 3, you can go to 1, and you can go to 2 also. So for 3, the answer is 8. For 6, the answer is 2. And for 1, the answer is 5. So what is the maximum along all this? The maximum along all this is nothing but 8. So this is all that you have to do. What do you have to do? You can do 4 things as I mentioned. Okay, if you are at an element X, you are going to take element X as it is, or you take the largest element on the left hand side. Let's say it's a Y. Now you can take Y as it is. Okay, this is one choice. Otherwise, you can take Y and then you can go to smaller elements and check what is the largest possible answer. Apart from this, you can go to a smaller element Z, basically iterate through all smaller elements Z on the right hand side and check what is the largest answer, because since we are calculating from right to left, we have already calculated for smaller elements that are on the right hand side. So you just go to the right, find all the smaller elements that are smaller than X, and what is the maximum element among all these. Now, you will ask that, Gaurish, this is nothing but a big O of n square solution, because for an element X, we are iterating through all elements and checking which elements are smaller than X and then finding their answer. Yes or no? This may be the largest element on the left hand side can be maybe maintained using a multiset. But how can we make this better? What are we trying to do? We on the right hand side, okay, we are finding all possible smaller elements and what is the maximum answer over all this. In mathematical terms, we can say that dp of index I is nothing but maximum of dp of j such that aj is smaller than ai and I is smaller than j. Basically, I is basically for all elements on the right hand side. If you have a smaller element, we just find the maximum one. Now, guys, there is a way to optimize this from O of n per iteration. You can see that here from I, we are iterating through all indexes j. Instead of doing this, we just want to find the range max query, okay, from ai plus 1 to ai minus 1 to 0. This can be done using a segment tree. Okay, what do we need to do? We just need to do a range max query from 0 to ai minus 1. Why this? Because in elements from in each element X, we are storing what is the possible maximum answer for value X. So if we generate a segment tree and we are storing the elements for, let's say, the value 5, we are storing what is the maximum possible answer, value 7, what is the maximum possible answer, so on and so forth. If we are at a possible value, which is 4, we check for what is the maximum possible answer for the element 2, not the index 2, for the element 1, the element 0, the element 3, and whatever is the maximum over all of this, we query. Okay. Now, that is all that we have to do. Ayush says, can you prove there will be only one continuous segment of elements reaching AI? So we need to find the segment. Okay. Great. This is a standard segment tree question. That is why I didn't really look into how you can do this in OFN. But with that being said, I hope you guys were able to understand the problem. Let me just share the code quickly and let me know if you have any doubts. This one, just 1 second. So this is a segment tree which just gives a range max and it also sets it. So what are we doing, guys? That we are iterating from left to right, and after it, we are maintaining a multi-set for the elements on the left hand side, right? Because as I said, we can go towards the left to the largest possible element because that is the most optimal greedily. Now, we just maintain a multi-set and you insert all the elements into the multi-set. Okay. So what is answer I? It is either the largest element in your multi-set right now, okay, or your current element. I have not removed it, so it remains the same. Or you go towards the right to a smaller element and find it. So basically, if you query 0 to AI minus 1, then or whatever maximum possible value is there for all elements between 0 to this number, we find that. Otherwise, what is the next kind of thing we can do? We can go towards the largest element towards the left, and then we can go towards the right towards the smaller element. So the largest element towards the left is ms.rbegin. So I just query for all elements between 0 to ms.rbegin minus 1, basically saying that you go to the largest element and then you query for all elements that are smaller than this particular element. This is a very simple dynamic programming update trick. Basically, instead of big O of n square dynamic programming, we are able to compute answers in a range because we found that our answer is either min in a range or max in a range. Such kind of optimizations can be done using a segment tree. And after we found the answer, we say that for all possible values that are between AI to N, okay, because guys, you can notice that if we are at an element, let me just show you. Okay. If we are at 5 over here, okay, and then you have a 7 over here, you have a 8 over here, and you have a 10 over here. Okay. So guys, for this 5, this answer is 10. Do you agree? If for this 5, this answer is 10, then for everything that is greater than 5 on the left hand side, basically 7 and 8, we are also able to reach 10, yes or no? So what we basically do is we just update the answer for all elements greater than 5 as well for 10. Let me just do a quick dry run to explain what the code actually does. I think it's a bit too advanced for people who don't know segment trees. So I'll just explain what exactly the code does, and then you can kind of solve it on your own. So we have elements between 1 to n. Let me just write it down. 2, 4, 1, 6, 3, 8, 5, 7. Okay. So let me have my answer for 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Initially, all answers is 0. We are iterating from left to right. Okay. For 7, the answer is what? Let me show you the code. The answer is either 3 dot query 0 to AI minus 1 or ms dot rbegin or 3 dot query ms dot rbegin minus 1. So the answer is either the largest element towards the left, which is 8, or answer between 0 to 6. You can see that everything is initially 0, so it is going to be 0. And we can go towards 8 and then towards a smaller element. So between 0 to 7. Okay. So answer is maximum of 0, 8, 0. So the answer remains as 8. Now guys, if for 7, the answer is 8, for any element that is greater than 7, the answer is also going to be 8 on the left hand side, of course. Okay. Now we say that the answer for this is 8. Now for 5 guys, for 5, the answer is either 8, okay, or answer between 0 to 4, or answer between 0 to 7, that is 0 to 8 minus 1. So the answer for this again becomes 8. And for all elements that are towards the right hand side of 5, we can say the answer would be 8. So we'll just store the answer here, which is 8. For 8, now this remains as it is. For 3, this is the uh, interesting part, right? So guys, for 3, the answer is either the largest element towards the left, or you can query from 0 to 2. It doesn't really help us. Or you can query, you can go to 6 and then query from 0 to 5. Basically, for you query what is the answer if I go to 6 and then I go to a smaller element. So you can notice that the answer is indeed 6 comma maximum of 6 comma 0 comma 8, because it was between 0 to 5. So this is 8. So that is why the answer here is 8. Now for 6 guys, you will query the maximum on the left hand side. So of course we would be updating this, and after that we would be querying on the left hand side. Maximum on the left hand side is 6. Otherwise you query from 0 to 5. Uh, okay, which is towards the right, which is 8, or you go to 6 and then so same thing, 8 comma 8. So the answer here is 8. Now for 1, you either go towards the smaller element, so you query from 0 to 0, nothing is there, or you go towards the larger element. The largest on the left is 4, and after going to 4, we can go towards a smaller element. So we are just querying for all elements between 0 to 3, and you can notice that between 0 to 3, as you can notice, 8 is there. My answer for 1 is going to be 8. Now similarly for 4, my answer is going to be 8, and for 2, my answer is going to be 8. Is this clear for everyone guys? This right here are not indices, these are values. Basically dp of x stores the maximum possible value right now for that possible x, and we are iterating from right to left and we are storing the answers. This was a quick dry run of exactly what the code does, because we have 3 choices. You can either stay right here, or go towards the left largest element, or go towards the left largest element and then go towards a smaller element, or go towards the right towards a smaller element. Okay, so that is more or less it for this particular problem. And you can solve this in big O of n log n time, because segment tree initializing it takes O of n time, and then querying a segment tree takes big O of log n time, and then updating it using a lazy kind of method also takes big O of log n time. So in big O of n log n, we are able to solve this very simply, and we are maintaining a multiset to store the smallest element, largest element on the left hand side. Is this much clear for everyone? If you have any doubts, feel free to ask the doubts. Otherwise, we can go towards the next problem, which is problem E. Like, have a look at the code and let me know what doubts you have. Okay. So guys, let's look at the next problem. Okay. Which is Penchick's and Chloe trees. Okay, it got accepted, which is great. This is one of my favorite problems. It required a lot of brainstorming, but very exciting problem. Let's see what the problem says. So Penchick and Chloe leave for Singapore. They could hardly wait to see the towering trees at the Singapore Botanic Gardens. So Penchick has a rooted tree consisting of n vertices numbered from 1 to n, with vertex 1 as the root. Chloe can select a non-negative integer d and create a perfect binary tree of depth d. Since Penchick and Chloe are good friends, Chloe wants her tree to be isomorphic to Penchick's. Okay. To meet this condition, Chloe can perform the following operation on a tree. Any number of times, select an edge u comma v, that is the parent u, so that u is the parent of v. Remove vertex v and all edges connected to v. And then connect all of v's children directly to u. We want to find what is the minimum depth possible such that we are able to bring up this tree. What does this mean, guys? Let me show you. Okay. So in the first test case, this is the tree that Penchick has. Okay. And we want to make this tree a tree that is similar. So if we create, what does the problem say? We have to select a D and then make a perfect binary tree of that depth. So guys, a perfect binary tree of that depth will look something like this. After this, what you can do is you can more or less remove a node, and for that node, what do? You remove the nodes and the edges and you attach the parent to its children. So after doing this operation, you can see that this tree became equal to this tree, right? So we just want to find the minimum possible D such that we are able to create the tree that is given to us. The problem statement is very simple, but coming up with the solution is actually very, very hard. Like this actually requires a lot of practice on trees and some ideas. Okay. So guys, how do we go about solving this problem? Okay. Guys, so the idea is we solve this problem bottom up. Okay. What do I mean by solving this problem bottom up? We can use DP on trees to solve this problem. And what do I mean by that? Guys, we find the minimum depth to make these leaves, and you can see to make these leaves the minimum depth is required as 0. So if you want to make only this, depth will be required as 0. For this, depth will be required as 0. For this, depth will be required as 0, and this for this the depth will be required as 0. Okay. Now for this node, guys, for this node, you can notice that for its children, okay, the depth required to make this is 0 and 0. So do you agree that these two can be merged into one? And since this is depth 0 and depth 0, with depth 0 plus 1, which is equal to 1, we can make this subtree right over here. Yes or no? Yes. Now, guys, the thing to notice here is that you can make this using depth 1. You can make this using depth 0. You can make this using depth 0. Now, what will be the depth required to make this? This is actually very easy. Like this is not this probably the hard problem, the hard portion of the problem. Guys, you can merge these two, okay? Because this might have come from an intermediate node which was removed. So these two can be merged into one, the smallest two. So you can notice that this required depth 0, this required depth 0. So we can just say that this came from a tree like this. This is depth 1 and this is depth 0. This is depth 0. Yes or no? these two can be merged into one of depth 1. Yes or no? Yes. Now, since you have two children and both of them is same, okay, we can just say that the cost required to make this is just depth 1 plus 1, which is depth 2. Yes or no, guys? Since the depth required to make this is 1 and the depth required to make this is 1, the depth required to make this particular thing is going to be 2. And hence the uh, answer for this is 2. Yes or no? Now let me show you how we can solve for some other thing, like let's say 112 and 112. Like coming up with this solution was really hard. I'm explaining right now that okay, this is the solution, but guys, coming up with this idea is not really easy. How did I come up with the idea? The thing is that if you are able to generate a subtree using the uh, data of what depth you required to make the subtree, you can make the parent. This is like a common idea in DP on trees. So after a bit of thinking, like 20-30 minutes, I came across this idea. And after coming up with this idea, the formula is relatively easy. I'll just show you all. Okay, let me just make this. So 4, 5, 6, and 7. Okay, so guys, this is the second tree. To make these nodes, depth 0 will be required. Okay, so depth 0, 0, 0, 0, 0. For making this node, depth 1 is going to be required because 0, 0. So you can have this as a binary tree and 1. Okay. Now we are left with a 1 which have 5, 6, 3, and 2. This requires depth 1 to make, this requires depth 0, 0 to make, and this require. Okay. So guys, can we say that these two are the smallest ones? Okay. We can merge these two and say it came from a common node. Yes or no? We can just say that this 5 comma 6 came from a common node and this requires depth 1 because these two require depth 0. Okay. Now, the smallest two are either this one and this 0 or this 0 and this 1. So you can just say that this came from a binary tree of depth 2. Why? Let me just show you all. If you create a binary tree of depth 2, okay, this will be 1, this, okay, and this will be 2. Okay, to create this 2, 1 was required. Okay, so, and you needed to create a 3. Do you guys notice, guys, if you remove these nodes right here, you will come up with this 3 which has in more or less depth 1. Yes or no? So if you wanted to merge two nodes, one has depth x, one has depth y, do you agree you can merge them into one node with depth max of x plus y plus 1? Yes or no? With depth 2, you are able to create these nodes. This represents 2, this represents 4, this represents 7, this represents 3, and you can just cut these off. Okay. Now, this has depth 2, this has depth 1. What is going to be the cost of merging these two into a tree? What will be the depth of this node, guys? Tell me. The depth of this is going to be 3, and hence the answer is indeed going to be 3. That is more or less the solution for this problem. This is for sure a 2000 or higher rated problem, but the basic solution is as it is. We are going to do a DFS call for node X. After that, we are going to compute the depths of all the children. And after that, we are going to use our greedy merging technique. What is our greedy merging technique, guys? Take two children. Okay, take two children with smallest depths required. Okay, let's say one is X and other is Y. You can just merge these two children into one with depth of maximum X plus Y plus 1. Okay, that is all that you need to do. And let me show you the solution of the same. uh, it might be like, the thing is, coming up with this solution was hard, but the implementation is not that hard. So you take in your tree and then you have a DFS call. You can see that in the DFS call, I am returning the depth required to make that node. So if it is empty, we are returning 0. Otherwise, we have a multi-set of children and we are going through all the possible children and we are inserting their depth. And after doing this, we can just say that the current answer is node.answer something. And after this is done, we can say that, okay, you're like, if there is only one child, then the depth is going to be that plus one. Otherwise, we do our greedy uh, merging where children dot size is smaller than one. We take the smallest and second smallest element. We remove them from our multiset. We insert them in our multiset with y plus one. And the maximum depth required for this is going to be maximum of node dot answer, comma. In the end, the children size is going to be one, or basically the depth required to make all of these nodes into one. So that is going to be children dot begin. So that is all that you have to do. If you look at, if you want to know what is the kind of proof required to do this, okay, let me just give you an idea of how you can go about proving it. Not a formal proof, but let's look at this case. Okay, the first thing to notice here is that the minimum depth required to do this is equal to the depth of the tree. Depth of tree. Okay, the second thing to notice here is that if you are at a node, okay, then if you look at the number of children, okay, then if you have four children, okay, and consider there was nothing below this, okay, consider there was nothing below this, we need to make a tree which has four children. Okay, now guys, what is the minimum depth required to do this? Do you agree? If I want four children, okay, only four children, nothing below this, just ignore this for now. You should see that the number of leaves in our perfect binary tree should be greater than equal to 4. So basically you can construct a tree something like this, and then you can just take this off and you will have this particular tree. Yes or no? Correct? Now, the second thing to notice here is that now we go ahead. Okay, we introduce that these are not nodes, but these are actually subtrees. Okay, and we need to merge these subtrees, right? Since we want to merge these particular subtrees, do you agree that we have to merge them such that these are disjoint subtrees? So all of these nodes, LCA is going to be this, and then each of these nodes is going to have pairwise LCA something. Okay. Now, the thing here is that this more or less works like binary addition. What do I mean to say by this? Like, what binary addition or something like that? It is always optimal to make small to large trees. And why is that, guys? If you have this tree, this tree, this tree, and then this tree, all right. If you go to add this tree over here, do you agree this is your node, this is that node, okay? And then you can say you can merge these into one, correct? But if you look at how binary trees work, or if you have looked at binary search tree, do you agree we are always trying to balance both of the children? Now, guys, if we want to make the subtree as balanced as possible, like we don't want to create a bamboo like this, right? We don't want to create a bamboo like this. We want to make the tree as balanced as possible. So do you notice it is always in our favor to go from the smallest towards the largest? Because if you merge these two, we will form something like this. And let's say we had one more single node over here. Then guys, we can merge these two over here. And after that, we can merge these two over here. And after that is done, all that we have to do is merge these two over here. And what is the cost? Like, what is the maximum depth required to do that? You merge these two. So this was, let's say, 0, 0. This became 1. This became 1. This became 2. Okay, this was 1. So it's maximum of 2, comma 1, comma plus 1. So it's 3. And that is all that we have to do. So we can just prove that while merging, it is always in our favor to merge from small to large, and hence the idea that we implemented, that you just have a multi-set, you take the smallest two and then you merge them into one tree, and that is all that you have to do. Coming up with this observation is not easy. That is why only 500 odd people were able to solve this in the contest. So that is more or less it for this particular problem. I hope you were able to understand this problem. Like, this problem was not hard to understand, but coming up with this observation was relatively pretty hard. So I hope you were able to understand problems A, B, C, D, E today, and I was able to do justice to your time. With that being said, if you did like today's post contest discussion, you can check out the TLE Eliminators 12.0 course. I will be teaching level 3 and level 4 this time, with topics such as segment trees with lazy propagation, dynamic programming on trees, dynamic programming, uh, tree, and more topics. So thanks a lot for watching. If you did enjoy, feel free to drop a like. If you felt that something could have been better, definitely let us know. It will help us improve. See you guys next time. Till then, bye bye. Thanks a lot for joining. Have a great day ahead.